Let's work on an example of implementing this problem-solving strategy for solving related rate problems. This next problem we look at is studying a relationship between speed of a plane and the rate at which the distance between the plane and a person on the ground is changing. We're told an airplane is flying overhead at a constant elevation of 4,000 feet. So if we try to draw a diagram, maybe we'd start off with saying the plane is over the man, 4,000 feet above the ground. The man is viewing the plane from a position 3,000 feet from the base of a radio tower. So we add a radio tower to our drawing, and we say the man is 3,000 feet away from the radio tower. The plane is flying horizontally away from the man. If the plane is flying at 600 feet per second, what's the rate between the distance? What's the rate representing the distance between the man and the plane? What's that rate increasing at when the plane passes over the radio tower? Now, in the diagram that we've drawn, these green marks, those are all constant values. They're not changing. Because the plane is flying horizontally, we know that it's always 4,000 feet above the man, even when it's over here, passing over the radio tower. That's still 4,000 feet vertical. So those values aren't changing. Also, the distance between the man and the radio tower, not changing. However, the distance between the man and the plane, that is changing. So when the plane was directly over the man, the vertical distance was 4,000 feet. Horizontal would be 0 if it's perfectly overhead. And then as the plane is flying away from the man, we can use a distance here to be the horizontal distance between the man and the plane. That is changing as the plane flies away from the man. The book is using x to represent that variable, so we're going to use x as well. And part of our step 1 process, let's write that out. The variable would be the horizontal distance. We're going to represent that using x, and that horizontal distance changes with respect to time, so I'm going to call it x of t. There's another distance between the man and the plane, and that's the diagonal distance. And as we watch the plane fly overhead, the diagonal distance between the man and the plane is changing. The book is using s to represent that. So we're going to keep that as s. Write that down, diagonal distance. Also changing with respect to time, so I'm going to write that as s of t. The horizontal distance changing with respect to time, that would look like dx dt. The diagonal distance changing with respect to time, that would look like ds dt. So the horizontal rate of change and the diagonal rate of change. Moving on to step 2, we're going to try and state the given information using the variables that we have. Now we're told that the airplane is at an elevation of 4,000 feet. We don't have a variable for that because it's not changing, so it's not a variable that we're going to put next to that, but we do have it in our diagram, so we're good. Also that the man is 3,000 feet away from the radio tower. No variable needed there because that's a constant. We do know the airplane is flying horizontally, so the distance between the man and the airplane is a horizontal rate of change, which is exactly the same as the rate at which the plane is flying. So our dx dt is equal to the 600 feet per second, the speed of the plane. We're asked, at what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? Well, notice that if we're looking at distance in the sense of direct distance, not just horizontal, then we're really asking about what is this diagonal distance between the man and the plane. So the thing we're solving for is ds dt, and we would like to know what that equals when that horizontal distance is equal to the distance between the man and the radio tower. Because when that horizontal distance x is 3,000 feet, then we know that the plane is right above the radio tower. Moving on to step 3, we need to find an equation that relates all of our variables. Now, if we're looking at our diagram that we drew, we might see that there is a right triangle popping out at us, where we have one side of 4,000 feet, one side, the long side, the hypotenuse, which is s, and then the other leg is that horizontal distance. And we know that for any right triangle, we can use the Pythagorean theorem, which says your hypotenuse squared is equal to the sum of the squares of the two sides. So we'll use this to create an equation that relates the variables from step 1. So our horizontal distance squared plus our vertical distance, which is 4,000 feet, that would be equal to our diagonal distance squared. Step 4 says to use the chain rule to differentiate both sides with respect to our independent variable. Taking the derivative of the left-hand side, we need the chain rule, where we first take the derivative of x of t squared with respect to x. Then we do the derivative of x with respect to t. Second term, the derivative of 4,000 feet squared, 4,000 feet with respect to t. Well, 4,000 feet is constant, so that doesn't change with respect to time. We put a 0 there. Then on the right-hand side of the equal sign, we have the derivative of s of t squared with respect to t. Again, the chain rule here. First, we'll take the derivative of s squared with respect to s, then we'll multiply that by ds dt. That related rates equation becomes 2x dx dt equals 2s ds dt. Notice that we have a factor of 2 on both sides of our equation, so we can simplify that if we want. Divide off 2 from both sides so that we have x dx dt equals s ds dt. Moving on to step 5, we need to substitute in the values that we were given so that we can solve for the rate we're looking for. dx dt is 600 feet per second, so we'll replace that. We're specifically looking for the rate ds dt when x is equal to 3,000 feet. So we will replace x with 3,000 feet. The diagonal distance s, we actually need to calculate that. We're not given the diagonal distance, but in the case where x, our horizontal distance, is 3,000 and our vertical distance is 4,000, we can solve that triangle. To find the s diagonal distance, which would be 5,000 feet. So we're going to plug in for s, 5,000 feet, and that's multiplied by ds dt, the value that we want to solve this equation for. So let's rewrite our equation up here. I have 3,000 times 600 feet squared per second. In other words, we have 1,800,000 feet squared per second. We're going to copy that over here. That's the left-hand side of our equation, equal to the right-hand side, which is 5,000 feet times ds dt. To solve this, we need to divide by 5,000 on both sides. The units for that 5,000 were feet, so I'm really going to divide by 5,000 feet. Which simplifies to be 360. We have feet squared per second divided by feet. That turns into feet per second, and that is our ds dt. So the rate at which the distance between the man and the plane is increasing by 360 feet per second as the plane is passing over the radio tower.